this lecture, I want to kind of give a sort of overview and kind of discussions of the main key points that you see for what is typically PN junction devices, or typically talked about as a PN junction diode. And so they tend to be devices that people see, and there's often a lot of mystery around these devices. But I want to talk about it, in terms of what do we see. And it's classically the case of I have a piece of N-type material and a piece of P-type material. And I put things together, and people are like, what's going on there? Well, it turns out there's a couple of key things in device physics that are important to know before you even begin that conversation. One is that you have to realize that in the silicon you have a band gap. And that band gap is 1.1 electron volts. And one of the key things the band gap gives you is the ability to have a whole range of concentration of free carriers, and you get effectively two types of carriers. You're like, well, wait a minute, what do you mean two types of carriers? Well, what you end up getting is you get this incredible silicon lattice and maybe some other non-silicon pieces that fit into this huge covalent structure that allows you to have effectively sort of a sea of electrons at one level, and a space which is like mostly electrons but just a few absence of electrons. These become positive charges. So I have this sort of sea of negative and positive charges that sort of act like a fluid in these spaces. And it's really kind of a neat concept. And you kind of move because you have available states and things that can work through in this space. And it's pretty neat to see what happens there. Now you can actually change this. And what people often talk about is doping, which may either be an N-type or P-type doping, is you're actually trying to, in a very specific way, sort of change what that relative concentration is. If you say it's N-type doping, which usually will be like a doping N sub D, you're actually putting in certain ions that give you more electrons in that space. Of course, those then give you positive ions when you're done. When you talk about P-type, you're actually doing places that are going to have absence of electrons, which basically give you holes and more positive charges, but then you get these negative ions sitting behind it. So the sort of play between these aspects is really very important. And really important to kind of see how that happens. Now when you look at this fluid and these basically carry of charge, you have two different things that are at play. One is electric field. So basically movement due to electric field. Other fields are possible as well, but we'll keep it to electric field here. In fact, you can argue that the current densities are related to the electric field by both the concentration and the mobility as well as the unit charge. This is actually another form of expressing Ohm's law. Really, current is proportional to applied voltage. It's very much the same question. And it's a way of kind of expressing that, but also realizing that the number of carriers has part of the impact on the resulting current. And then there's this whole other question about diffusion. And diffusion basically says I'm moving in the opposite direction of the gradient. Now you might go, wait, if it's opposite direction, why is there not a sign there? Well, partially because charge is always the movement of positive charge. Well, N usually is dealing with the electrons, so there's a double negative here. So just be aware of that. If you did this for the holes, you would actually get a negative sign there. And so as a result, what happens with this very interesting structure, and it's classically thought about, imagine I have a piece of N-type material and a piece of P-type material over here, and I say, what happens when I put it together? And what's going to happen instantaneously is that I'm going to have electrons and holes rushing across. If you've done structures where you've said, let me have a semi-permeable membrane in chemistry where I have different concentration of ions, it's a very similar question where I'm actually getting charges that'll move across, but then there's some electric fields that push back because of the charges. And you get an equilibrium there. And what ends up forming in almost all of these cases, is I get a depletion region, a region where I have fewer electrons and holes. In this case, if they come together because one's an absence of electron and one's an electron, they kind of eliminate each other. It sounds really crazy, but it's basic and amazing. It's just like it kind of disappear. But what you end up finding is that you have a region in here where it's just the exposed ions. And remember, the exposed ions do have charge, so I could actually integrate over that and I'd get an electric field and potential. And as a result, I can talk about having electric field, which then changes the barriers. Now, when you talk about having a band gap, what you mean is I have a region that's a conduction band and a valence band, and there's a gap in here. That's roughly 1.1 electron volts in silicon. And this gets interesting because it does allow me to kind of separate these, and I can say, oh look, I've got areas for electrons, and the way you draw this is actually an increasing electron energy. So electrons want to roll down the hill, so they see electric field, they roll down. Holes like to go up hills in this space because, again, it's increasing electron energy, so it's decreasing hole energy or positive energy, so they like to roll uphill. This gets kind of fun when you look at the details. And what you see is that there's a whole bunch of carriers here, and they can diffuse across, but only those that are above a certain energy level. Well, how would I know what energy level? Well, there's a whole kind of discussion. You can get into this much more carefully, but in a simple case, I know that carriers are distributed in an exponential format. This is actually a Fermi-Dirac distribution function. This comes from statistical mechanics. You can derive this from first principles, understanding that there's only 2 carriers allowed in a particular state, and you work your way through the opportunities. Well, it turns out if you look at this carefully, you actually get a decreasing exponential relationship when the energy is greater than the Fermi level. And so what it means is that there's an exponentially decreasing number. The term that you're looking at there is KT, and if you relate that to charge, that becomes an energy level UT, which is KT over Q. It's roughly about 25 millivolts at room temperature, millielectron volts if it's just KT. Okay. And so this works out to be that you actually get this interesting barrier to play with here. And only the carriers that are above a certain height, above the barrier, do that. And what will happen is then if this is what I would get if I didn't apply any voltage across these devices. If I took these 2 things that I moved together and then I, on the edges, applied voltage to it, I can tweak this barrier. And by tweaking this barrier, then changes the current. And notice things are exponential, right? Exponential in the distribution. So if I change the voltage barrier, I expect an exponential change. In fact, this is exactly what I get in a major part of the region. You can actually see a nice data curve out of this. And as voltage over UT, there's the curve fit that goes through it. This is in the region that's forward bias. And as a result, you get this sort of very nice symbol for a diode with voltage across and a current going through it. This is a really sort of look over p-n junctions over the whole, just in sort of a snapshot. Each of these things could easily be detailed lectures unto themselves, but it gives you kind of a roadmap and an idea of where these things are coming from. And if you're using p-n junction devices, this helps you, basically diodes, it helps you get a sense of, well, where are these things coming from and why would I imagine getting the kind of relationships that I'm talking about here?